At its core, Grover's quantum search algorithm achieves astonishing speedup over classical techniques by leveraging the counterintuitive properties of quantum superposition and entanglement. It allows searching an unstructured database of n entries with only O(n) queries to an oracle function that recognizes solutions. This squares the probability amplitude in those states, precipitating their measurement. The technique relies on three key components: initialization of an equal superposition state, an oracle to flip the phase on solutions, and a diffusion operator that amplifies marked states through constructive interference. By iteratively applying the oracle and diffusion, a measurement will reveal a solution with high probability after around P4n iterations. In a digital logic circuitry context, we can think of n database entries as 2n bit strings indexed by n qubits in superposition. The oracle would flip the phase on strings representing solutions. Measuring the amplified state allows accessing the solution with far fewer checks than classically needed. While revolutionary, Grover's algorithm faces limitations in practice. It requires a coherent superposition across all entries, relying on quantum RAM models difficult to realize physically. As with many quantum algorithms, precision requirements impose an overhead for quantum error correction. However, the algorithm enjoys asymptotic optimality. No possible quantum solution can achieve more than a quadratic speedup. Mapping Grover's technique to real-world applications requires reformulating problems into database searches or function optimizations. With quantum computing still in its infancy, we must creatively recast challenges to align with present hardware capabilities. Potential use cases include optimization tasks like logistics, financial modeling, AI, and quantum chemistry. In the NISQ era, Grover gifts a glimpse of quantum computing's awesome potential, but realizing practical speedups remains an active area of inquiry during this age of noisy, intermediate-scale devices. Still, each incremental hardware gain further solidifies Grover's status as a keystone of quantum algorithm design, destined to power a future born upon waves of probability through once impenetrable complexity. At the heart of Grover's counterintuitive speedup lies a resonating insight. We can choreograph constructive interference through repeated superposition, allowing solutions to ripple outward and amplify above an ocean of noise. Yet channeling this potential requires navigating treacherous straits between theoretical shores and practical shoals. Grover's algorithm transcends conventional computation by deftly steering quantum resources into interference patterns that boost improbable outcomes into measurable realities. It concentrates diffuse probability into narrow bands encoding desired solutions. Mathematically elegant in theory, yet demanding extreme precision to manifest physically, even for small instances. These opposing poles tug at attempts to harness Grover's algorithm today, stretching possibilities while revealing fragilities. Noisy intermediate-scale quantum devices now boast tens of qubits, tempting application to useful combinatorial searches. However, maintaining the delicate superposition dances mandated by Grover remains beyond current hardware capabilities. The slightest environmental disturbance introduces errors cascading across the algorithm's repeated interference steps. Where does this leave practical application in the NISQ era? Creative problem embedding provides one bridge across the theoretical-practical divide. Rather than directly applying Grover search, we can reformulate tasks to work within the constraints of near-term quantum resources. Useful problem classes include recommendation systems, path optimizations, financial portfolio optimizations, and quantum chemistry solutions. In these cases, we compromise some performance for attainable demonstration on early quantum computers. Yet, we must equally avoid overpromising current quantum machines, acknowledging the hard limitations of coherence bottlenecks today. Instead, Grover's algorithm beckons as a guiding star, an ultimate exemplar of what quantum computing may achieve at full fault, tolerant scale. Its quadratic speedup and optimality anchor our long view of a future untethered by noise, free to tackle challenges inconceivable to classical techniques through fluid maneuvers in quantum state space. For now, we channel fragments of this algorithmic potential while pursuing the hardware advancements